Advanced aliens really are out there, and we have enough data to say roughly where they are in space and time, and when we will meet or see them. There is no consensus here on Earth that we have detected ET aliens, either near us or greatly far away. Yet a vast universe should birth enormous numbers of technological civilizations, TCIVs. This apparent absence of ETs is known as Fermi's paradox. One space astronomy site has compiled a list of 16 distinct theories that explain the paradox. A new approach, independently developed by two different research parties, uses mathematical modeling to reach surprising, in fact epic, conclusions. There have been three main approaches to ET life. I'll call them if, what, and when. If asks about solutions to the Frank Drake equation. It describes the major hurdles evolving life must solve on the way to becoming a technologically capable civilization, call it a TCIV. It tries to guess how many places alien life will exist and how far they will evolve. What speculates on what will they be like? Aggressive or peaceful, carbon-based or not, biological or machine, humanoid or icky. The when approach concentrates on the vast amounts of time left in the universe. As in, when will alien civilizations appear and how far will they disperse in the universe? When I ran across a tweet about the latest breakthrough, it was about the when. I wasn't surprised to see that it was only covered mostly in science blogs, and not at all in the popular media. The approach is what scientists call abstracting away details. Assume that the ifs and whats will vary a lot, so don't worry about them. Bug-eyed monster or machine overlord, it doesn't matter. Instead, infer what we can from some simple assumptions and a large helping of mathematical modeling. The new work started with 7 papers from a physicist, S.J. Olson, as he said, operating from the outskirts of academia. Media coverage was shallow. It focused on the gosh, gee whiz, but not at all new, idea that advanced life might take over the universe. It ignored his math-heavy arguments about how, when, and why. Late in 2020, the same general approach was used by an eclectic team: an economist, a theoretical physicist, a machine learning, AI, scientist, and a financial analysis programmer, aka a quant. The main author, economist and polymath Robin Hanson, made a bigger splash with his paper. A provocative blogger on many topics, he was building on his work of 2 decades ago. Hanson is part of Oxford's think tank, the Future of Humanity Institute. He had impacted the alien story years earlier by naming the Great Filter. That is the unknown set of circumstances that makes spacefaring civilizations rare, and which might be a threat to our long-term survival. Both Olson and Hanson believe that their independently produced work makes their similar conclusions much more plausible. The models say that someday a limited number of expansion-driven TCIVs will so modify enormous parts of the universe that the change will be easily detected from Earth. Earth's TCIV has shown up extremely early in the history of the universe. Any powerfully expanding aliens are so far away that we can't see them yet. But there are very likely a lot of them. When we first do see the earliest signs of their existence, it won't be long, on a cosmic timescale, before some of them will be here, right on top of us. That's because they will spread at a large fraction of the speed of light. The universe will eventually fill up with TCIV life. You can see it happen in this animation based on the science. The threefold path of alien civilizations. The major assumption of the theory is about the life branches that face any TCIV. All new origins of life that pass the Great Filter and thus become a TCIV can go one of 3 different ways. 1. They can, sooner or later, die out. 2. Or, they can go into some kind of steady state, maybe stagnating, maybe hiding, maybe disappearing into a virtuality or subliming into some exotic dimension or state of matter. They are quiet, in the sense that other TCIVs are unlikely to detect them. 3. Any other TCIV will be expansionist, and will expand across its galaxy, and perhaps across other galaxies, until it meets another expansionist TCIV. What expansionists who meet one another will do doesn't matter to the model. But the model does assume that within space controlled by an expander, no independently new TCIVs would arise. An expansionist TCIV both expands to new star systems to control new matter and energy and to prevent any new TCIV from competing in that space. Maybe an expanding TCIV allows existing quiet TCIVs to persist, and maybe it doesn't. Hanson calls the expanders grabby aliens, they grab resources, or loud aliens, they make changes that are detectable at a great distance. The expander TCIV itself he calls a grabby civilization, GC for short. You might object that a highly evolved T-Civ would not be expansionist, out of consideration for other sentient species. That's fine. It only means that they are one of the quiet ones. You might then argue that, given human experience, quietness is a virtue, that different kinds of life should not dominate one another. Maybe you are hoping that every species will adapt Starfleet's prime directive. Olson's and Hansen's models, though, suggest that expanders, simply by definition, will eventually prevail. Our position of being early to the party might mean that we might become one of the expanders ourselves. Or not. It's like the three elements of a crime: motive, means, and opportunity. You could say we have the motive, must expand to survive disasters, and can probably develop the means for interstellar travel, but we might not survive long enough to have the opportunity. One advantage of thinking about time, the when, with regard to aliens is that the universe is very young compared to how long it might last. The Big Bang was 13.8 billion years ago, and Earth formed about 9 billion years after that. This is early, if for no other reason, that in the early years of the universe many stars exploded, sterilizing their planets. So there hasn't been that much time left for life to arise on the remaining planets. The latest estimates say that the universe is likely to last 200 billion years, and maybe much more. Hansen notes a possibly longer lifetime based on stellar evolution. So, while the age of the Earth or the age of the universe seems like a big number by itself, remember that the universe will hang around at least 20 times longer. That needs to be our frame of reference for cosmic civilizations. The large numbers, fed into the when simulations, lead to a highly plausible, if alarming argument. There are or will be a lot of technological species. We know that evolved life tends to expand to fill as big a niche as its environment allows. So there ought to be some T-Civs with an unbounded appetite for expanding their territory. Distance is not a barrier to unlimited expansion in space, given the great amounts of time available. Even if most T-Civs stop expanding at some point, it would take only a few, or even one, unlimited expander, a grabby civilization, to fill the entire universe. This has big implications for life of any kind, anywhere. A T-Civ that stays in its own backyard, like a solar system, or a smallish group of stars, will only affect that backyard, an extremely tiny piece of the universe. In truth, even a T-Civ that occupied all of its home galaxy, hundreds of billions of stars, could be considered a minor player, unless it kept expanding. There are, after all, hundreds of billions of galaxies. Over time, GCs occupy volumes of space and keep expanding those volumes. What does this mean for any other T-Civs that they may run across? We need to add a sixth point to the list. When a GC expands over a volume of space, it will prevent other T-Civs in that volume from becoming expansive. This point seems true by definition to the theorists who have considered it. Either a newly contacted T-Civ will be destroyed, or it will be somehow contained in its original habitat. Or, all the resources it would need to expand will be taken by the newcomer. Or, it will be absorbed into the newcomer. The contacted T-Civ will not go on to become a GC itself. So, a seventh point that is an assumption of both lines of research: a GC would radically modify any area that it controls. Olson says that, as a limiting case, a GC might convert most of the local matter to energy. It will be totally obvious if you are living in an area controlled by a GC. If not immediately, then sooner or later. A few lame UFOs or nightmarish anal probings are not the behavior of a massively hegemonizing GC that overruns galaxies. So, we are not, yet, in a controlled area. The above speculations are certainly an important new theory in the science of extraterrestrial life. But the real cleverness is in the mathematical modeling that allows conclusions about life in the universe and our eventual connection with it. The trick is to do simulations while varying important parameters fairly widely. You then find conclusions that are true across a range of parameter values. In other words, true no matter how you run the model. Both Olson and the Hansen group started with known data to estimate important parameters, such as how many difficult steps must occur before primitive life becomes technological, or how fast a T-Civ can expand its control through space. They then ran numerous simulations, varying those parameters. How can this approach contain enough factual information to be sensible? One reason is that the modeling process uses knowledge that astronomers and cosmologists have accumulated about the physical size and evolution of the universe as a whole and of its many parts, like galaxies, stars, and planets. An example of the modeling process is how it handles the difficulty of becoming a T-sieve. On Earth, we think the important steps were things like cellular life, multicellular life, and big-brained tool using. Hansen's new study bypasses questions of exactly what the critical steps are in passing the great filter to become a T-sieve. Instead, it assumes that there is an unknown number of hard steps to become a T-sieve and thus potentially a GC. The simulations vary the number of hard steps and use a range of times they might take. These estimates are anchored by assuming that our planet's age is a typical example of how long it takes to become a T-sieve. Becoming a GC would take further steps than we have made, so the model then adds more variation to account for that. Another example of the kind of reasoning that simulations can support is how they explained Fermi's paradox, our being unable to see evidence of distant GCs. The sims say that it's likely that GCs already exist, and more are to come. But they are so far away that their evidence, traveling at the speed of light, has not reached us yet. This can only happen if we appeared very early. The Hansen Group's calculations say that Earth is at least in the first 10% of all T-sieves, and we might be way earlier than that. Think what it means that the Earth is especially early in the race to evolve civilizations. It confirms that we are rare, that we're special. Hansen's team said that humanity is likely the first T-sieve in our galaxy of at least 100 billion stars. What are the odds that we make something out of being so early to the party? Hansen points out that our sun will expand to swallow the Earth in another 5 billion years. If something descended from humans wants to survive past that time, then it will have to physically move on to somewhere else. But his other predictions are that we will be touched by a GC long before that. If GCs arise from non-grabby civilizations, NGCs, a depressingly low transition chance, approximately 10 to 4, seems required to expect even one other NGC ever active in our galaxy. The quote is another surprising inference, and one that is pessimistic about humanity's future. I will try to translate. The more often GCs arise from new T-sieves, the sooner they would get to our galaxy, and be visible to us, or even take over our space. Since we do not see any, the rate of conversion from T-sieve, aka NGC, to GC must be pretty low. The model suggested the chance of conversion to be at best 1 out of 10,000. But we are a T-sieve, so like the T-sieves, our odds of becoming a GC are that low, too. There's one other interesting conclusion, which I shall call the bug on the windshield principle. Famous blogger Scott Aronson, interpreting Hansen's work, said of it, "Once we can see them, it's too late." To understand this prediction, you need to accept the idea that a GC could expand its territory very fast, at some large fraction of the speed of light. Perhaps this sounds ridiculous, but physics doesn't forbid it, we just don't have the technology. The most logical way is via high-speed probes that reach a new territory, b. drop off technology that starts consuming the resources to saturate the local area, and c. make copies of themselves, the probes, to expand further outward. Both teams cite expert analyses that make this type of expansion plausible at a high fraction of light speed. Olson even found a possibility that a high but sublight speed front of saturation, added to the universe's expansion speed, would mean that colonization, the saturation front, effectively moved faster than light. Nobody would ever see that coming. But Aronson noted that, even under Hansen's assumption of sublight speed expansion, when we saw the light signals of an oncoming GC, it would not be very long at all before the aliens were actually upon us. This is not long, as measured on a big time scale. However, if we only had 500 or 5,000 years warning, would we have time to prepare to meet a species capable of colonizing galaxies or galactic clusters? We'd be the bug on the windshield of a supertanker.